Hey guys, welcome to 6.4 Potential Energy, the next piece of our potential energy or work in energy unit here. So today we're going to talk about potential energy and how we use it. So first off, a quick definition. Potential energy is basically energy based on its surroundings. So if kinetic energy was energy due to movement, potential energy is kind of due to its surroundings. So some familiar ones that we know about: a spring that's wound up, a stretched elastic band or rubber band, or an object move at some height above the ground. And that's kind of the basics that we'll use here. So for potential energy, we have an object that's sitting on the ground. We know it has its mass, and let's assume that we're holding it up or we're going to raise it. So in raising a mass m to a height h, the external work by the work done by the external force is Fd cosine theta. And so once again, we've already kind of done this. D is the displacement up. The external force is holding it up. So the angle between those will be 0 degrees, so cosine of 0 is 1. And when we crunch the numbers here, we essentially get mgh, or mass times gravity times the height that we lift it. Other times you'll see it kind of like this: the second y position minus the first y position. In other words, the difference between the two. We therefore define gravitational potential energy as mgh, and this is where the object is lifted up a certain distance. So we had some examples where the fireman was climbing up the ladder. So we kind of found how that worked. Well, this is kind of the shortcut to those kinds of questions. So once again, potential energy is energy due to its lifting up. Once again, we have the y2 and y1. Those are just the differences in the height that the mass is working on. So this potential energy can become kinetic energy if the object is dropped. Remember, we had our skater simulations. You guys did a great job on. So potential energy is a property of the system as a whole because it depends on an external force to move it from. So where do you measure from? So it really doesn't matter. We're really concerned with the changes in the energy system. And so depending on the type of question we're looking at, where we start measuring kind of dictates how much energy is in the question that we have. So this is examples of using the height of an object to figure out what its potential energy is. But we also have a spring. There's a couple of different things that we use for the spring. So here's my little animation here. I've compressed the spring with a little mass, a ball at the end of it, and then when I let it go, the ball is now moving with kinetic energy. And so that whole, if I drop the object, it increases speed. Well, if I compress the spring, then yes, the ball will shoot out also. So when it's compressed, we have a little way of thinking about it. We have this unstretched spring, a stretched spring, and then a compressed spring. When we start measuring these, we kind of start the unstretched distance as my origin. And so when I stretch the spring, what I'm doing is I'm getting that point and I'm providing a force external to it, so I'm pulling it away, which means the spring has to pull backwards towards itself. If I compress the spring, that means I'm pushing down on the spring, and the spring must try to push me outward. So depending on whether I'm stretching or compressing a spring, the spring is either going to push me away or pull me back in. So the formula for this is pretty straightforward. The force required to compress or stretch a spring is defined as this: Fs, or F spring, sometimes you'll see elastic, is negative kx, where k is a spring constant, and it needs to be measured for each spring. And then the x is the displacement from the original unstretched position. So a K value dictates how strong a spring is. So rubber bands might have smaller K values, whereas the springs in the suspension of your car has a very high spring constant. So once again, the higher the K constant, the greater the force it's going to spring. And of course, the distance we pull will also tell us how much force is involved there. So as the force increases, the spring is stretched or compressed further. We find the potential energy of the compressed or stretched spring can be written as such. So we'll see potential energy due to the elasticity, or PE sub spring, is defined as 1/2 kx squared. So we have two kinds of potential energy. We have gravitational potential energy, which is mgh, and then the potential energy due to a spring, which is the 1/2 kx squared. So once again, all of these ways to define potential energy, and we have to kind of sift through the problems in order to look at what we're looking at. And just knowing that the potential energy can be converted to kinetic energy, and way more on that later. All right, thanks for listening. Catch you guys later. Bye.